Welcome back to the course C# Advanced Language Features. I'm Philip Ekberg. You've reached the final module of this course. You should be extremely proud of yourself for making it through this entire course. We've covered so many important topics that will make you a better developer. In this final module, we'll continue on that path and talk about how to clean up resources and learn a little bit more about garbage collection. C# is a managed programming language. This means that you don't necessarily have to worry much about memory management. In some cases, though, you can use components that allocate unmanaged memory. It's wise to follow certain patterns and practices to make sure that you do not have unnecessary allocations stuck in memory. The garbage collector will look for objects and memory that you no longer need. This could be an instance that you created in a method. Once that method completes and the instance is no longer relevant, the garbage will be collected. You do not have to manually force the garbage collector to run. You could, and this is only appropriate if you create something that manually allocates unmanaged memory. Instead of forcing the garbage collector to run, we should trust that it cleans up resources for us whenever it determines that it's necessary. We can still run into situations where we'd get what looks like a memory leak. The term memory leak in .NET can be a little bit ambiguous. What I mean is that we have allocated memory that will eventually be collected by the garbage collector, but is living in memory longer than it should. A memory leak can also be objects that are unable to be collected by the garbage collector because they are still referenced. I'm talking about the situation where you have an event handler that holds a reference to an object that is no longer relevant, but it cannot be collected. We saw an example of this in the module on events. We need to make sure that the event handlers are always unsubscribed. Otherwise, the garbage collector will think that the object is still relevant and it won't clean up that resource. When you terminate the application, the memory will be freed as well. So the term memory leak refers to objects that are allocated in memory longer than they should. Eventually, most of these objects will be collected. For the components that use unmanaged memory, which most streams, bitmaps, and graphical components do, you should follow a very basic pattern to ensure that the memory is cleaned up when you are done. In the warehouse management system, I now want to load all the image data available in a certain directory. I'm going to introduce a method in the Windows application that loads all these files from disk. This method will return an IEnumerable of bitmap. This requires us to install a NuGet package. We can ask Visual Studio to do this for us. Then, let's call this load images. This method will look through a directory that I have added to the project. Each item in this directory will be copied to the output directory. For each file, we are going to read all the bytes. To create a bitmap out of this, we need to pass a memory stream. We can construct a memory stream that uses the byte array for its data. The bitmap will use unmanaged resources. And if not used correctly, we may end up having a bit of a memory issue. This code does not follow the best practices for how to work with streams of data or bitmaps. We'll improve this soon. But first, we need to understand why this may be a problem. Let's use yield to create an iterator. That way, we do not have to create a temporary list of bitmaps that we later return. This is a cleaner way of producing a stream of data. We can now call this method. Let's do this in the click event handler. Then let's iterate through the collection of bitmaps and print the size of each bitmap to the debug window. Let's run the application with the debugger attached. Let's make sure that we open up the diagnostic tools in Visual Studio. This will show us the memory usage. Each time the button is pressed, the amount of memory increases. It looks like it never recovers. The application continues to use more and more memory. Eventually, some of this allocated memory may be collected. Depending on the application, your code may use additional memory that you simply cannot afford. If you process a lot of data, doing it like this may lead to memory being allocated for longer than it should. You may even run out of memory if you're not cleaning up after yourself. You don't know when the garbage collector will start collecting, and you shouldn't run it yourself. There is a better way to approach this. So how do we clean up after ourselves in this situation? Each resource that uses unmanaged memory or needs to clean up after itself should implement the disposable pattern. Bitmaps, streams, and other types that want to clean up when they're done implement something known as iDisposable. To indicate that we are done with our resource, we can introduce the using keyword. This can be used in two different ways: a using statement or a using declaration. The using declaration will ensure that the method dispose is invoked when the method has completed. In our case, we have two resources that both implement iDisposable: the memory stream and the bitmap. The memory stream can be cleaned up right after we've used this to construct the bitmap. We can assume that the bitmap used the data that it needed to create its own internal structure. If we only dispose of the memory stream by adding a using declaration, it won't have much of an impact. The big problem that we saw with allocations and the memory usage comes from using the bitmap. Since the consumer of this method expects a stream of bitmaps, if we dispose of the bitmap inside this method, anyone that uses this may end up in a little bit of a pickle. They won't be able to use the bitmap because it's been disposed and destroyed. All unmanaged resources will have been cleaned up. Instead, it's very important that whoever consumes this stream of bitmaps will also be in charge of cleaning up after themselves. In the for each loop, where we use the bitmap, we can add a using statement to define that we've used this bitmap. We can go ahead and dispose of managed and unmanaged resources. With this very small change, let's rerun the application. Now, it doesn't matter how many times you spam the button. The memory usage looks much better. You no longer have allocations in memory that are no longer necessary. This is why it's extremely important to clean up your resources. We'll also look at implementing the iDisposable interface later. You can also introduce a finalizer. A finalizer is called when the garbage collector is ready to collect the instance. Remember, you don't know when this is going to happen. You can use the finalizer to make sure that resources are being cleaned up. But in most cases, you want to rely on the disposable pattern instead and introduce the iDisposable. This gives the consumer of the class the capability of determining when to clean up what could be expensive resources. It's good to keep in mind that the finalizer will only be called when the garbage collector is ready to collect the instance. This means if you have an event handler leak and the instance cannot be collected, you may be left with allocations that you do not need. The syntax for the finalizer is simple. It looks like a constructor, but is prefixed with a tilde. You can introduce a finalizer on an object in the application and experiment with this on your own and see when this is executed. Next, we are going to look at how to implement iDisposable.